All right, welcome back to CE 529. So I have your tests on the desk there. It's sorted by last name, so feel free to pick them up. And if you are not here right now, that's okay, because yeah, I'll have them in the lab as well. And what we are going to talk about is get started on a new topic, which is, again, a little bit of a relationship between micro level modeling and macro level modeling. Micro level, where you are looking at sort of movement and ingress and egress of each agent or each vehicle, versus what you might do in a macro level, where you treat everything as a sort of a flow, as a flow of as the fluid might be flowing. So let me go ahead and share the screen. Okay, so as you can see, the queuing theory part is sort of the micro level part, and then the shockwave modeling is the macro level. And again, we'll try to still see, like we did when we were doing the car following models, we'll still try to establish some sort of consistency, or is there a relationship between the two? Are they consistent with each other? And we did see that there is that consistency between when we did the car following. I think we'll try to do the same thing here. Okay, and is there a way to reconcile the two approaches, one being the queuing theory and the other being the shockwave modeling? So what we're going to start off with is sort of very basic 321 type queuing theory stuff that you might have seen. So traffic queues, so this is sort of the motivation for all of this, right? Traffic queues form at intersection, at roadway bottlenecks, especially during congested periods, and they are a source of a considerable delay. Obviously, queuing theory is not unique to traffic analysis. You have retail stores, service-oriented businesses, bank tellers everywhere. You have sort of an agent serving other agents or users. There you'll have some application of queuing theory. And then what we want to see is we want to derive some measures of highway performance, including vehicular delay, when we are trying to analyze these queues. So that sort of is the objective. And obviously, this is not to say that, being able to analyze these queues actually leads us to solution for these queues, because obviously solutions are a little bit more long-term, a little bit more planning oriented, even maybe relating sort of other disciplines like housing and land use, and all of that comes together. But our purpose here is a little bit narrower in nature. So we're not trying to solve this necessarily. We're just trying to figure out, okay, what is actually happening, so we can get a handle on measures such as total delay, measures such as queue length, and then all the things that sort of get derived from that. It might be operations related, it might be safety related, a lot of different things. So we are just trying to get the performance here, highway performance under a queuing regime. So if you're talking about queuing theory, in queuing theory, we are looking at queuing models, and what we are interested in are following things, or at least what we want to know beforehand, before we do any type of analysis, is these three things. The first one being the arrival rate. Okay, so the arrival rate being so arrival date denoted by lambda. It's deterministic or uniform distribution or exponentially distributed. So you could have it where you're assuming completely deterministic arrivals, or you're assuming some sort of a random components to that. And we've seen that in vSim. When we do any kind of input traffic in vSim, it asks us, do you want, I think the default is sort of this exponential distribution. So you specify, let's say, 3,600 vehicles per hour rate. It's not that every run of the simulation will discharge at that rate if you specify that stochasticity in the model. Okay, and that's what we mean by M, exponentially distributed, or some other sort of exponential distribution is a good measure of how sort of traffic arrives at a location. It's a good distribution for that, but you could have other sort of random distributions as well. But that's not to say, even though the realistic situation is where you'll have the exponential distribution, this is not to say that anytime you're using uniform distribution or deterministic distribution, that's completely useless. In fact, that can be very useful because a lot of times when we are doing intersection delay analysis, we actually look at completely deterministic models, and then sort of we add a penalty that we want to add just for having sort of stochastic arrivals. Okay, so even though exponential models or stochasticity-based models of arrival rates are more appropriate and realistic, they're computationally more challenging. So a sort of a hybrid approach that we take is that we always do deterministic distributions assumption at the beginning, and then maybe add a penalty for the delay, just sort of add the delay because, you know, sometimes the capacity won't be fully utilized, and sometimes intersections might get oversaturated. So we just add a delay penalty to that. So that's why deterministic arrivals are, or arrival rates patterns are also sort of useful. And what is the key implications of deterministic arrival rates is, if you assume that, what happens is, if you have a 3,600 vehicles per hour arrival rate, you can translate that easily into 60 vehicles per minute. Okay, so 3,600 vehicles per hour, you can derive that into 60 vehicles per minute, or you can do 1 vehicle per second. So these are the things that you can assume if you assume a deterministic pattern of arrival. That every minute there will be 60 vehicles, and every second there will be 1 vehicle. Obviously, that's not how traffic works in reality, and that's okay, because we know, because there are studies that have told us, like, okay, what type of penalties to apply for more stochastic arrivals and so forth. Okay, and then you have the departure rate. So this is like how fast you can serve. So let's say, think about this. If you're at arriving at a theme park gate or something, and it takes whatever time it takes them to give you a brochure or check your ticket or whatever. Let's say it takes 30 seconds on average, and you can assume deterministic departures again. So every minute they will be able to serve 2 parties or 2 customers, right? So that's the idea of the departure rate. How much time does it take to serve you? And based on that, you figure out how many passengers or how many cars or how many sort of travelers could be served per minute or per hour and so forth. Okay, so that gives you the idea of your departure rate. So this departure rate typically represented with a mu. And again, you could have deterministic or uniformly distributed. Last but not the least is number of departure channels. Typical departure channels would be just 1. So if you're talking about, like, let's say traffic signal, even if you might have multiple lanes, typically when we are analyzing an intersection and the vehicle departures from that intersection, we treat departure channels S to be always 1. Okay, even if you have multiple lanes, because we know that all of those through lanes will be green at the same time, we just treat them at the same departure channel. Now, you could have multiple departure channels in traffic, though. I think we've talked about it. Maybe we mentioned it at some point. Can anybody think of a situation where there might be multiple departure channels in traffic? Obviously, grocery store line, there are multiple departure channels, right? There could be 2 or 3 or 4 checkout lines, although these days with labor shortage, it's hard to find any more than 1 line being available. But be that as it may, so in traffic, can you think of situation where there might be more than 1 departure channel? Yeah.
But if there's an intersection where you're coming and then there's like multiple options to go, like
multiple options to go, but
from
as
the same lane.
Like if you're turning left onto.
But see, the left lane typically, so that's a good point. Like, if you have turning left lane or right lane, for example, right? But I'm not sure if that's what you're referring to, but let me address this point. What happens if there are left and right turn lanes? So typically we'll analyze those two sort of separately. So their arrival rates and their departure rate would have to be analyzed somewhat separately. Yes.
Well, what if it's one of those lanes
Yeah.
That's kind of like asking like, what would be the implications of that? Like, would that be
Right.
multiple departure channels for one?
Typically, if they are being served by the same signal cycle, because ultimately where this application gets most used is when you're trying to sort of look at when you sort of have a green time, how many vehicles can depart in that green time of the vehicle. And because that all lanes will be green at the same time, yeah, they are typically sharing the same green time. So we treat them as one departure channel.
So
But could there be another example? Just think.
Like everyone's like first one, like one
Yeah,
get into the circle, but then like if there's maybe like a bypass lane.
yeah. The only yeah, I think you can think of it that way, especially if you're talking about not a signal where where not all of them have to be served by the same green light thing. So you could have a situation. So that could be one situation where you're approaching a roadway entity and they're both being served by the same, not necessarily green light, because obviously there are no lights on roundabouts. Typically they're not. So yeah, so you could have a situation where there could be the vehicles arriving, and that sort of gets to what you're saying, but not at a signal that's being served by the same green light, but maybe in situations where you're coming up to the same lane points and then you're sort of departing out if you're turning right. So then that way, potentially what you might be doing there is you might be looking at the through and the right to be combined together. So that would probably, so you can think of those as multiple departure channels if you can then somehow combine the through and the right turn demand. So then you have, for those total combined demand, you have sort of two departure channels. Okay. Yes.
What if you were looking at like a freeway and
Uh-huh.
then it like splits off? You could go like, I don't know, 3 ways. Like,
Right.
would you look at all of the lanes together as one arrival and then look at the 3 departures separately, or would it be by lane?
It depends on the context though, right? Because the problem with there might be that the flow might be at the same, like the demand rate or the arrival rate might be the same for the total flow. But if there is sort of divergences between how many people are turning right, how many going 3, how many turning left, then you might have to analyze those 3 demands separately. If you can somehow combine the demand, if your analysis context is such that you can look at all of that demand as a total, then you could think of that as sort of 3 different departure channels. So serving 3 different demands, or no, serving sort of same demand with 3 departure channels. But typically what happens in those applications is that we start to think about those 3 demands as sort of differentiated demands. Like, the right turn demand gets separated from the left turn or through demand. So typically we don't look at that. Yes. Right turn, so that's what I'm saying. Like if you are treating the demand separately, then those 2 right turn lanes and through lanes would have to be the demand would be your arrival rates, right? So if you're treating those 2 arrival rates, then those 2 departure rates also would have to be treated differently. So they will be they won't be like 2 departure channels, as much as there will be 1 departure channel for the through demand, 1 departure channel for the right turn demand. So only ultimately but if you do combine the demands, if you combine the both demands, and then you're looking at both demands combined together, then you could think of those as 2 different departures. Does that make sense? That's fine.
Are you looking at a left turn?
No. Oh, yeah. So if you're talking about a toll plaza, then yeah, left turn and right turn basically. So right turn, but I think the left turn would probably have to go in the inside lane, right? They would probably want to, yeah, because otherwise that lane might exit there. Depends on the exact geometry of the roundabout. So what you might have to think about is how are my demand distributed by lane? And if they are sort of coming into the same lane, up until that point, I can treat that as the same demand with their own exclusive departure channel. Right? So that's sort of, I was thinking of a simpler example of a toll plaza. So toll plaza would be a place where you could have multiple departure channels even within the same streams, right? And sometimes even within departure channels, you could have sort of two e-pass lanes, you can treat them as the same departure channel. You could, if you wanted to, unless, but like you, in the toll plazas where you have sort of some manual lanes and cash lanes, they will be their own departure channel and they will have their own sort of arrival rates and departure rates and whatnot. And then you could have your e-pass or like easy pass lanes and stuff like that. That could be your own departure channel as well. Okay. So yeah, there are examples of multiple channels. They depend on the context of your lane combinations and stuff like that. But then also a more simple example could be toll plaza, where you might be looking at different ways of departing traffic. Okay, the queue discipline always is first in, first out for traffic. So if you're ahead, then you leave first. You come in first, you leave first. That's your typical first in, first out type of queue discipline. And again, this is another problem if you're treating all lanes as the same, but you have reason to believe that your right lane drivers are much less aggressive. Typically, that doesn't happen. Typically, we don't assume that, at least in our modeling purposes, even though that might happen. So in the modeling, we don't account for that. But let's say you're combining the two departure channels, but the right turners actually slow down more compared to through ones. Then your first in, first out assumption starts to get a little bit violated. Because if the right turns are taking longer and you're treating them at the same demand level, then that could be a problem. So then you may be better off treating them as sort of like, they're coming in combined and then they have two departure channels. And the second departure channel on the right has a little bit sort of lower demand rate. So you don't want to you always want to be making sure that this first in, first out assumption still is reasonable, even if there might be some less aggressive, less sort of more defensive drivers on right lane or whatever. Overall, if you want to be not in a too big of a violation of your first in, first out discipline. Yes.
So when we're looking at first in, first out, last in, first out, is it kind of like we're analyzing a segment of runway to see the vehicles that enter first and exit first?
Right. So yeah, so you could have, like, the longer the segment, the more opportunities there are for somebody else to overtake. So typically, when we are doing queue type analysis, we assume that we are always dealing with sort of one point in location. So this queuing theory, that's a good point actually, because whenever we do analysis based on queuing theory, we look at, because we want to obviously look at this first in, first out sort of queue discipline, we're typically analyzing these queues at one location. We're very interested in one point on the road a lot of times. Queuing theory typically will assume that you are at a node and you are analyzing the queues at that node. Actually, this will come back for us when we talk a little bit more about the relationship between the queuing theory and the shockwave model. We'll come back to this exact point as to how queuing theory talks about queues at one location, and then shockwave can actually give you the spatial extent of the queue. Yes.
If it's a red light, but right turn,
Yeah.
that would be a second departure.
Yeah, it says I wouldn't call it a separate departure channel as much as I would think about it as a different demand serving a different queue. That might be your best bet, and that's why you probably need the lane as well. So that could. So I think you're almost better off treating that as sort of a separate demand being served by a separate channel. Sometimes what we do is, sometimes if we have to combine the demand, what we do is we sort of add a penalty to the right turning vehicle. Sometimes, even if the light is green, they're going to be a little bit slower. So when we're doing like queue delays analysis, we treat each right turning vehicle, if they're all happening from the same lane, we make each right turn vehicle to be like 1.15 times a through vehicle. So that's basically add a 15%. They will take typically 15% more time. And same thing, left turn, we add an even heftier penalty. So sometimes we do those types of things and talk about that a little bit more in traffic engineering. Yeah. So we represent the queue as sort of like these hash marks, and then with three things: distribution of inter-arrival times, distribution of service times, and number of servers. So typically, this DD1, D stands for deterministic for the arrival times. This D stands for distribution of the service times, and then 1 stands for the uniform distribution of the uniform distribution of service times, and then you have 1 server or 1 departure chain. Okay. Now, if I said a queue discipline is like MD1, if I said the queue discipline that you have going on is MD1, what does that tell you? That tells you that your arrivals are distributed stochastically. You have sort of an exponential distribution for arrivals. For departure, you still have deterministic distribution, and you have 1 departure chain. Okay. So if I did like this, M/M/3, that means you have exponential distribution for the arrival times, exponential distribution for the service times or the departure times, and then you have 3 departure chains. In this class, we'll still deal with DD1 queuing regime for now, because again, that analysis is really helpful to us, because most analysis in your traffic engineering, in your highway capacity manual, a lot of times the analysis will be based on these DD1 queuing regimes, and then adding in some sort of a penalty, specified penalty given the intersection geometry and a whole host of other factors. Just add a penalty for exponential arrivals and departures. Yeah. So you should know what these sort of labeling stands for, what this labeling stands for, but you will always, solving problem time, you'll always deal with this DD1 queuing regime. Okay, so let's, and this example is something that you might have seen before. Okay, you must have probably seen this in your, let's see, in your 321 class. Does this ring a bell, this type of an example? Anybody? What do you think? Have you seen something like this before in 321? No? Okay, that's fine. If you haven't seen it, that's altogether good anyway. Yeah, that tells you that I haven't taught this class in 6 years. Anyway, so DD1 queuing regime. So we're talking about how do we analyze the delays at a location. So this is entrance to a national park. There is a single gate where each driver receives a free brochure. The park opens at 8 a.m. and at that time, vehicles begin to arrive at the rate of 480 vehicles per hour. After 20 minutes, the flow rate declines to 120 vehicles per hour and continues at that level for the remainder of the day. So initially, people arrive faster because everybody gets there at 8 o'clock, and then sort of the flow rate declines. If the time required to distribute the brochure is 15 seconds, so when the ranger gives the brochure, says hello, good morning, whatever, takes 15 seconds for each driver to get their brochure. The question is whether a queue will form, and if so, how long is the maximum queue? How long is the maximum delay? And let's see what the last thing is. When will the queue dissipate? When will the queue dissipate is the last thing. Okay, so now let's think about this. Okay, so let's think about what is my still see the problem. I want to do this. I don't know. So let's start talking about. First, let's think about what is my arrival rate here. So what is your arrival rate? And then you could see that arrival rate is not a constant, right? It changes after a certain period of time. When does the arrival rate change? After 20 minutes, right? So at 8 a.m., let's call, first thing that we assume in these types of problems is that whenever sort of things start to get interesting, so in this case, when the park opens at 8 o'clock, let's call this t equal to 0 at 8 a.m., right? So let's assume that first, that our time equal to 0 at 8 a.m. My arrival rate is 480 vehicles per hour. And then typically, because all the action is in minutes, in terms of like, after 20 minutes, the flow rate declines to 120 vehicles per hour. So let's assume the time is measured in minutes. So I would like to get my arrival rate in vehicles per minute. What is my arrival rate at t equal to 0 in terms of vehicles per minute? 8 vehicles per minute, right? And remember, I can do this because I've made that DD1 assumption. That because my arrivals are deterministic, I can translate 480 vehicles per hour into 8 vehicles per minute. Okay. And that rates enforced is what time interval when my arrival rate remains 8 vehicles per minute. What is the time interval during which this is the arrival rate? 0 to 20, right? So I can write it as 0/t 20. That makes sense? So I can say that between t is equal to 0 to 20 minutes, this is my arrival rate. What happens to the arrival rate at t greater than 20? So anytime after t equal to 20 minutes, what happens to my arrival rate? It becomes how much? 2 vehicles per minute. That's right. That's t greater than 20. Okay, can I write an equation for, in terms of time t, in terms of number of minutes since 8 o'clock, can I write the total number of arrivals as a function of time? Okay, so I want to write, so I wrote the arrival rates here. So I want to write the equation for number of arrivals in terms of time t. I want to write number of arrivals as a function of t. Can you tell me what that equation might look like? Number of arrivals as a function of t. Number of arrivals is how many vehicles have arrived at any given time t.
Do you have a piecewise function?
We will have a piecewise function, yes. But how would you start off with? What would you start off with? What will be your first piece of that function? The arrival rate times t, right? So I would say number of arrivals, I could write that as 8 times t. That makes sense? And then this will be applicable 0 to t. What happens at t greater than 20? Okay. Okay. Make sense? We'll come back to this. Okay, now let's talk about the departure. So I'm going to write on this side, I'm going to work on perhaps. I'm going to work on the departure here. But before we get to departure, let me talk about this. So let's check these functions. Do they work? Because I want to see number of arrivals as a function of t, right? How many vehicles do you think would have arrived by t equal to 10? How many vehicles would have arrived by the time t equal to 10? 80, right? That makes sense. 8 times t, we got that. How many vehicles would have arrived at t equal to 20? 160, that's good too. Okay, so you're applying the top equation, right? 8 times t equations, you're applying this equation, that's perfect. But now let's think about how many vehicles would have arrived at t equal to 21? At t equal to 21, how many vehicles would have arrived? 162, right? But your equation says 2t. If I plug in t equal to 21 in this equation, do I get 162? I don't. So that means when I'm writing this number of arrival equation, that equation is not quite correct, right? So what's the problem? Yes. That's exactly right. So if you're representing the total arrivals, you should say it's 160. That's the vehicle that would have arrived within that t equal to 20-minute period. So you have to account for those. And then not just be 2 times t, because even this is not correct. Because if you plug in t equal to 21 here, you won't get 162. You'll get 160 plus 42, which would also be incorrect. So you have to account for the fact that this new arrival rate has only been in place starting at t equal to 20. So this is how I should write my total arrival equation. Okay, so whenever you're writing these type of sort of these discontinuous functions for total number of arrivals, you should be careful about this. Yeah? How you write that down. Now it's not that all the time arrival equations will change. It could be that departure equations change as well. It could be, but this is what the equations are going to be. Yes. 160. So 160 is because we are trying to write the total number of arrivals as a function of time. So when we go any time more than 20, let's say t equal to 21 or 22 or 25, whatever, we have to account for the total arrival that happened before when the arrival rate was 8 times t. So 160 vehicles arrived in the first 20-minute period, and that's what we had to add on to. So it's like this 160 essentially is 20 times 8. So if that makes it any clearer, we can make it 20 times 8, or maybe 8 times 20 is probably better even. Just as a representation purposes, 8 times 20 plus 2 times t minus 20. Now I think we can do the same thing with the departure rate. What is the departure rate? What is my departure rate? I want to still get it in terms of vehicles per minute. 4 vehicles per minute. Departure rate is 4 vehicles per minute because it takes 15 seconds to distribute that brochure to the drivers who are coming in. So I will make this 4 vehicles per minute. And then this value is for all values for all times t, right? Because all values of t, this is basically what the departure rate looks like. So I think this is a good news for us because we can, if you want to write down number of departures, that should be a very simple equation. What would that look like? Number of departure equation at any given time t. 4 times t, right? That's it. So I wrote down these number of arrivals and number of departure equations. What is the purpose of this? Because ultimately I want to find out what my queue lengths and so forth look like. So I want to get those estimated. So I needed number of arrivals and I needed number of departures. So the first question is whether a queue will form. So queue can form anytime number of arrivals exceed number of departures. Okay, that's the definition of the queue. So if you want to define queue length, it's always arrivals minus departures. Subtract the departures from arrivals. Arrivals minus departures. So anytime arrivals exceed departures, I will have a queue. Okay, and I can see that between t equal to 20, 8t exceeds 4 times t. So I will have a queue. Yes. So the answer to this question is yes, there will be a queue right? Because arrivals exceed departures. So I will have a queue. Yes, that's true. Now I want to find how long is the maximum queue. So let's see if we can write down the queue length expression. What is the queue length expression? Can we define, would queue length be a discontinuous function or sort of like a singular function, like a, would it be a function that has breaks, or would it be a sort of a continuous function? Queue length expression. We already know what queue length looks like, right? It's arrival minus departures. It will be a piecewise function. That's right. Piecewise is the word I was looking for too. So yeah, it will be a piecewise function that will have a break at t equal to 20, because between 8t minus 4t will be the queue length for first 20 minutes. This will be your queue length, right? But then once you've hit that time, what happens at t greater than 20? Still, the expression would still be the same though. It's still arrivals minus departures. It's just that my arrival equation has now changed to this one right here. So I'm going to say 160 plus 2t. Okay, so that's my arrivals. Let's check the math here. Okay, does this make sense for t greater than 20? So what I did was I wrote down these expressions so what would happen is that initially the queue will be building up. But when the arrival rate goes down to 2 times t, or it becomes 2 vehicles per minute, then the slope of the arrival curve will change. And then the departure curve will be going at the same time. So then you will be able to derive what is your maximum queue length. Okay? So what time would the maximum queue length would occur? T equal to 20, right? Because that's the point where the departure rate reduces. And now you have fewer vehicles coming in every time. So then the queue length will start to shrink, because now the departure rate exceeds the arrival rate. Now you can have more departures. Okay, so how long is the maximum queue? Can you tell me now? At t equal to 20, what's the maximum queue length? How many vehicles would be in the queue? 80, right? At that point, 80 vehicles will be a queue, because 160 would have arrived, but only 80 would have left. Okay, and then when will the queue dissipate? Let's try to answer the last one first. What do you do to figure out when will the queue dissipate? Queue goes away at that point. So what you do is you take the queue length expression. What do you do to this? What do you do to this expression, queue length expression? You set that equal to 0. That's right. So 160 plus 2t minus 40 minus 4t equal to 0. And if I solve it, I get t equal to 16. Okay, please check the math there. So at 9 o'clock, 8 o'clock, 60 minutes will be 9 o'clock. At 9 o'clock, the queue would have dissipated. And what would happen after 9 o'clock? Now, no queue, just, vehicles will be coming in. The ranger will take 15 seconds to give the brochure, hang out for 15 more seconds, and then maybe another vehicle will come in, give the brochure, hang out, things like that. So the things are not very interesting after 9 o'clock to us, because, the queue has dissipated. Everything is great. Now,
Wait, sorry, could you Say, how do you get the max delay formula?
I haven't yet done the max delay. This is just the queue length formula.
Oh, what's the 40 from? Sorry.
This 40?
Yeah.
So I did this, simplified this expression. So 160 plus 2 times t minus 20. So I said, I wrote it as
Oh, I'm sorry.
160
Okay.
plus 2t minus 40 minus 40. So this part is the arrival part. This part is the total number of arrivals. And then I subtracted departures.
Okay, sorry.
Yeah, no, it's fine. Yeah, all good. Okay, now let's think about, so this is just the queue length. So when there's the queue over. When does the queue go over? Okay. Now let's think about maximum queue. When the maximum queue will be? Yes.
Do we ever end up using the 15 seconds?
We did use 15 seconds. We did use 15 seconds somewhere. How did we get the departure rate? Right? Because we remember we said 4 vehicles per minute. So the question was, how do we use this? When did we use this 15 seconds? We used it right here to get our departure rate. Because it takes 4 vehicles can depart every minute because of this. 15 seconds per vehicle. So 1 minute is 60 seconds. So 4 vehicles per minute. Okay, so the next thing is, how long is the maximum delay? So now maximum delay is interesting because delay is, so just like queue length is defined by arrivals minus departure, the delay is defined as what? If the queue length is arrivals minus departures, how would you define delay though? How would you define delay? Yes.
Like the maximum speed.
Yeah, that's exactly what we are going to do in terms of how we define that delay, how do we derive that value for the delay. I'm more interested in, just like I defined sort of a fundamental formula for queue length, arrivals minus departure, can we have a similar sort of construct for the delay? What does that look like? How do you define delay in this context? Waiting time, right? So what would you call it in terms of, so could I say the delay is basically departure time minus arrival time, right? So I can figure out for any vehicle, if I can figure out the arrival time and I can figure out their departure time, that will be my delay, right? Now, because delay is defined this way, departure time minus arrival time, I just have to figure out, and then the vehicles are arriving one by one. So I can figure out arrival time of any vehicle, and I can also figure out the departure time for any vehicle as well. So let's first do that. Let me ask you this. What is the arrival time? At what time, at t equal to what value, 80th vehicle would arrive? If I want to find out what time would the 80th vehicle arrive, can you give me that value? What time would the 80th vehicle arrive? T equal to 10, right? Because I have 8 vehicles per minute. That's good. Okay. What time 1/20th vehicle would arrive? 1/20th. $15 is correct because 15 minutes. How do I get that? Because I know 8 vehicles per minute are arriving. 1/20th vehicle would arrive at t equal to 15 because 15 times 8 gives me 120. I can get those times. But it could get tricky to figure out what time vehicle arrive after what point. After 20 minutes, that means 1/60th vehicle is simple to derive. But any vehicle after that, I have to apply the second equation rather than the first. Right? So any vehicle after 1/60th would be, and then similarly, if I want to find the departure time is more simple because I can just do, because there is no equation change, it's always 4 times t. So what time does the 80th vehicle leave? what time does the 80th vehicle leave the mix? What's that? Yeah, because 4 times t is 80, t equal to 20. So before we do the max delay, can you give me delay for 80th vehicle? I'm just curious if we can derive this. A delay for 80th vehicle. What's that? 10 minutes. Yeah, 10 minutes is the right answer. How you get that is that you get the departure time for the 80th vehicle, which will be 4 times t equal to 80. So departure time is t equal to 20 minus the arrival time, which was t equal to 10. 20 minus 10. Basically, the departure time for the 80th vehicle is 20 minutes. The arrival time for the 80th vehicle is 10 minutes. So that means they're delayed by 10 minutes. Okay. And then this delay for that, any vehicle will keep increasing. Can you now think of which vehicle will experience the most delay? Yes. Yeah, one that comes in when the queue length is at its max, right? So basically you join the queue at the back end and you are at 160th. You are that 160th vehicle. So all you need to do is just derive the delay for the 160th vehicle that arrives when the queue is maximum. So you can probably figure out the delay for the 160th vehicle. Vehicle arrives at t equal to 20. No, it arrives at t equal to 20. When does it depart? When does the 160th vehicle depart? Equal to 40, right? Because the departure rate is always 4 times t. So to figure out the delay for the 160th vehicle, you figure out departure time. For 160th is t equal to 40 minutes, right? Because 4 times t equal to 160. So I'm going to say 4t equal to 160. That means t equal to 40 minutes. And similarly, I can do arrival time for 160th vehicle. We know already that. Is 4t, no, not 4t. It will be 8t equal to 160. That means t equal to 20. So max delay is 40 minus 20. Again, always remember the fundamentals. Queue length is arrivals minus departures all the time. Delay is defined at departure time minus arrival time. And then the max delay is experienced by vehicle that comes in when the queue is at its max. And after that, queue starts to decrease. So anybody who comes after that will have shorter amount of delay. But you can derive the delay for any vehicle. And the queue goes away at t equal to 60 minutes. So no delay after that. So if I ask you, what is the delay for the vehicle, any number of vehicles that arrives at after t equal to 60 minutes, they will not face any delay at all. Right? So that's the idea. So you can actually represent this solution graphically. So I'll show you in the next slide here. You can represent this solution graphically here. And I'm going to stop. I know time's up almost. That your departure rate is represented by this curve right here. Okay. And then your arrival curves are right here. They go above the departure curve. And that's where there is a queue. So you have on the x-axis, you have vehicles, number of vehicles. On the y-axis, you have the time. Okay. So I'm going to stop here now. We'll come back and pick up this discussion. We'll try to relate it with shock waves in the next class. I'll probably try to wrap this up in next, not this week, but the next week, okay? All right. I will see you in the lab. Anybody who hasn't gotten their test? You almost did it, correct? Because you only found like one threshold. So Freeway is not completely correct.
Yeah.
But and what you have here is also correct. But you didn't check for the second threshold. You didn't check for whether both routes will be used or not. You see what I'm saying? Between R1
I
and
just didn't write it down.
You did? Okay, yeah. So I didn't.
Because I had to know these equations will work.
Yeah.
Because if they didn't, okay, because this is what, even if you split the 100,000 here, it's going to mean.
Yeah.
You're left with 2.8.
Yeah, that's what I needed to see.
2.4.
That's what I needed. That's why I only took 2 points off of the question.
Okay.
I needed to see that threshold check because remember we talked about this threshold only gives you Freeway is not competitive, but it doesn't, at least by itself, doesn't tell you whether both routes are used. Right? So that's all. That's all. Okay. Yeah. So yeah, yours is almost correct. You said Freeway won't be used.
Yeah.
But you didn't tell me. That's what I was telling him also. Remember, we only eliminate the freeway. Only eliminated the freeway, but we haven't yet established that both of these routes. So these equations, you see what I'm saying?
Yeah.
So you have to establish
Okay,
that.
I have to establish the other threshold.
Yes, exactly. That's what you're missing. That's only 2 points.
Oh, okay.
So yeah, I should have said that here.
Yeah. It could, even though it could be obvious.
Yes. But
I need to.
yeah, I didn't know that you know.
Right.
Because especially because I'm not asking for a solution. So you won't be able to check because
Oh,
if you don't check it, yeah, I know you derived it, but you know,
I
I didn't ask
didn't
for a solution, but I needed to see that because you know, sometimes you can get negative answers and figure it out.
Yeah.
But yeah, I needed to see that.
Okay. So I'll have to like
So now
the threshold we're using R2 is
right,
yeah.
whatever it is. So that's why, and it exceeds, it's higher than, I mean, it's lower than 1.8 or whatever.
Right. Yeah. Okay. And what's the point? What's the
47. You got the 47, and so you double it, it will be 94 in now.
Okay. So 50.
Yeah, out of 50. Yes.
Thank you.
All right, perfect. Okay, I'm gonna take this off, right? I gotta run. Okay. Yeah, I think we do cover sometimes in traffic also, we cover that.